So officially recording. And uh, so we're recording today is the 27th of Wednesday, making sure everyone can hear me here. I'm going to talk a little bit about some things I looked at this week, but Benjamin had a good question. We're doing some property stuff. We always do some property stuff at home. My wife left her job, hang out with our kids, and basically we have a couple pieces of property that we have in Guilford County. And so if we type in the word, we won't type in the word Mulrooney here, but during the pandemic, right before the pandemic started, I was driving to work from Greensboro and I saw this like piece of property, this dilapidated house sitting right on this parcel right here. And I just drove by and it was owned by an old woman and it had like a paper like taped on the front door that's like, if interested, call this number. I'm like, okay. And everything was like overgrown. It was disgusting. And people had like lived there. Like it was like $700 a month house. So like you can imagine it had like rats. It was this 3 layers of carpet, all this stuff in it. And so what we did was my wife and I were like, hey, let's just make an offer to the lady for 4 acres of land and this crappy house and like see if she'll do it. And you don't have to deal with real estate agents because has anyone dealt with a real estate agent before? You have to basically pay them 6%. So, if you buy a house for $200,000, you're losing $12,000. $12,000 is just disappearing into the ether to pay for that. So I try to do all my own real estate too. So, which is not the best idea, to be honest with you. But we spoke to this lady and just said, hey, we're going to offer you this. So I wrote up a contract and all this other stuff, and we bought this house. And so we lived there during the pandemic, and we've got another house down the street that we call our quote unquote big house. And we rented that out to some people who didn't destroy it as much. We had another house in the city that I lived in before I married my wife, and I rented that one out that got destroyed by people. But this used to be all one parcel right here. And towards the end of the pandemic, we're like, hey, this would be a great place to build a new house, because this is 4 acres right here. I don't know how much acreage costs around here, but I can imagine it's probably pretty, expensive. You know what I mean? Probably, the acre plots go for probably, $60,000, $70,000 an acre. So this thing's like just the land alone is probably worth a couple $100,000. And we bought it for, half that, and it includes the house. But so we went and had a survey done. So some of the things that your GIS people do for a living, because you notice these numbers are different, like 138937, 138938, 138935, but this is 236087. And so we went and got a survey done and basically petitioned the county so we could create a whole brand new parcel right here, And so if you work for the Durham GIS or Guilford GIS, this is basically what you do for a living. You do a real specialized set of going through and changing the geometry based on the surveys and looking at this information and all that other good stuff. One of our former students named Zuri, has anyone met Zuri before? Tall guy, used to be a geography bowl. That's what he did. And so now when we click on this thing right here, you can see our names, all that other stuff. This is the assessed value we pay taxes on, our information. We've kind of moved, we moved down the street or whatever. And so we use this as basically an Airbnb, which is pretty good. So like every night we collect, like 80 or 90 bucks for this, but you got to go and clean it out and all this other stuff. And then in our other house, we have a basement that we also Airbnb. So that's like 50 bucks a night. Does anyone use Airbnbs and stuff? No, you do? Are they good? Most of them are good? Yeah. They're pretty cheap. Like I don't think I've ever used maybe once or something like that. I don't know, but my wife, she does it all. And, at our other house has a separate basement and it's like, I don't know, checks keep coming in, but you got to go clean it and all that other good stuff here. But you can see some of the GIS stuff kind of going on here with the creation of a new parcel. And then you click on this right here. You click on this thing right here, and then you can see information about parcel IDs, all that other property addresses right here. So we had to go and petition to get a brand new physical address, which is a pain in the neck. So hopefully we're gonna build a house right there, sell the other house and then keep this one. And one of my kids is really emotional about us. He wants that house. And I'm like, what? Like, what's want mean? I'm not charity. You know what I mean? You know, that's a couple $100,000 house that, so that might be a difficult conversation in the future because it's a really good source of income right now. But we're trying to rent it out short term just because traveling nurses and things like that. But the one thing I did want to talk about today before I got into the position paper was on Monday, I went to this symposium here over at UNC Chapel Hill. And I think you'll see these kind of floating around here, especially being here around UNC and Duke and NC State, and even hosted here at Central once in a while. But this was Places, Environments, and Health Symposium. And I thought this was good because basically talks about the idea of places, geography. And I think it's a central theme to this class. And so I'm going to talk about a couple of things that we saw here. The thing I liked was it had lunch, it had coffee, it had breakfast, like free lunch, all this other good stuff. But the most important thing, you go into these things because there was an online version, is that if you have a choice of going online or going in person, what do you think you should do? Go in person. Why? Why did everyone say in person? Because you get the free lunch? I'm going to drive an hour to get free lunch? I could network, exactly. That's the most important thing. And so when you go to these places, it's to go and network and meet people. Facilitating relationships is important. It's really easy for me to ignore your email. Really easy. You me to ignore your email as opposed to me looking in your face and saying, well, thank you, we're going to go with someone else. Or, hey, it was nice meeting you. You're just an email at some point in time. But when you go and meet these folks right here, it's good experience. And hey, I remember that person from Central, or I remember that person from UNC, because this was a symposium. As you can imagine, it was basically the use of geostatistics in health, environment, and, basically mapping. So they talked about a lot of neat techniques. They talked about things like inferential statistics, which is the big fancy word that we're going to start using here in about 15 minutes. Like clustering, hotspots, Geostats, Moran's eye. These are all things that you're hopefully all going to learn because, and they talk about means and standard deviations and modes and all that other good stuff. And so these were some of the things that we kind of looked at today. This one I really like. This was evaluating rural mortality disparities in cancer. And basically, this person, Dr. Kinzik, associate professor for the Department of Surgery at Boston BU, basically looked at how do we measure rural? What's the definition of rural? Well, I see, this is really asking some big questions here. What's the definition of rural? Can you tell me what it is? What's rural mean to you, Sanaya? What's it mean to you? Small? Okay. What's it mean to you, Ariel? Country. How about you, Benjamin?
Low density.
Low density. How about you, Alondra? Not a lot of people. Okay. Excellent definition. Now, the thing about that is, how do you measure rural in a map in GIS? Because what I look for is what are all the numbers that we can associate that. So there is a population density component. And we wrote a paper recently, it came out at the beginning of the year, as to the different definitions of rural. We found like 9 different definitions of rural, but this woman here had 15 different definitions of rural. Really based on population density, scale, meaning, all right, there are just certain counties that are rural as opposed to zip codes and block groups and census tracts and blocks that are rural. And so, all right, this county's rural. So there's maybe 40 urban counties, another 30 micropolitan counties like Greenville or Asheville, which are cities, but just not big cities connected to other big cities. And then the rest are basically rural, like Bladen County or Columbus County, or whoever, some of the more rural counties out there. And so doing cancer research, we're like, what's the best definition of rural? And we've done some of that before where they look at things called RUCAs, rural urban commuting patterns. So where are the commuting patterns? If you're going from a rural area to an urban area, is it really rural? Not really, no. If you're a rural area, staying in the rural area, that's rural, because basically you're contributing your time, resources, energy, money, funding, whatever else to that urban area. And so it kind of got into these rural urban commuting patterns and things like that. But this was the use of statistics and geostatistics for these here. We had some lightning talks, space water models. This one right here, guy at Ohio State, was really interesting in terms of looking at the built environment. When I use the term built environment, what's that mean? We talk about environmental science all the time, right? What's environmental science? Our department is environmental science. What's it mean? I'm looking at Alondra. Alondra's just spinning around. What's environmental science to you all? We got Ariel. You do environmental science for a living.
All the science.
Chemistry, yeah. Environment's impact on the actual environment, soil, water, air quality, whatever. But when we talk about built environment, we're talking about the actual structures, buildings, infrastructure, all those other things. And he did a really neat project in New Jersey where they did Google Earth or Google Maps, where they like put little person there and looked around the area right there to look at the built environment and to look at cancer risks. And like, what are things, when we talk about built environment, they talk about you put yourself in Google Earth, you stick yourself at a corner right there. How do you know if it's a good neighborhood or a bad neighborhood? What are some indicators that tell you that?
Like as far as like the environment?
Yeah, the built environment. The built environment. Trash. What are you going to say, Ariel? What's that? Factories. What are other things when you say, oh, this isn't such a good neighborhood right here? What are some things you think of or say? Crime. What about the building, the actual houses? Are they nice houses? They have boards on their windows. And so he created a tool or an indicator that says, hey, let's randomly select a whole bunch of blocks in Newark, New Jersey, and Essex County and look at the quality of the built environment. So you got your little Google Earth person there and you went through a little checklist and said, are there any boarded up buildings? Yes or no. Is there any garbage? Yes or no. Is there any graffiti? Yes or no. What is the quality of the growth brush? Basically people who mow their lawns versus not mow their lawns or whatever. And then the quality of the houses, meaning are there gutters falling off and all those things. So you got a whole bunch of yeses and nos combined with poor quality, high quality, low quality, whatever. I think they had about 4 different classes, and they attached it to a number and then measured some type of cancer risk with that. And as you can imagine, basically the lower quality neighborhoods or whatever had higher cancer risk. Now, a lot of times, what came first? The chicken or the egg, or the behaviors that you might see attached to low quality built environments, kind of confounding with cancer risk. Who knows? But I thought it was really neat. It was a really big effort in data development. We created this neat little tool here. This one was good here. Determinants of health. A lot of times we hear about SES, low SES. Has anyone heard that term before? SES? Socioeconomic status. And these days in North Carolina, especially when we talk about Central, we talk about the idea of SES disadvantage or marginalized or disadvantaged communities. And one of those other papers, they also looked at the idea of advantaged communities, SES advantage. And they're not totally opposite things, meaning, well, if this is low income, then SES advantage is high income. They saw like more professional and white collar jobs more associated with this SES advantage. And so they kind of created this SES disadvantage and look at health metrics and attached to those. These were really good. Spatial causal inference, wildland fire, smoke effects, and health. This guy teaches over at NC State, so it was just amazing here. So if I think of it, especially moving forward after the semester, these are always good places to go and meet people and speak, get free lunch. I spoke to this guy. I was trying to hook him up with a couple of our students to take some classes over there because NCCU has an interinstitutional agreement with Duke, UNC, and Chapel Hill. So you can go and take classes over there, especially grad classes or computer programming classes, GIS programming classes over there for the same price it is to go here. And so some of these classes are online, but I always strongly suggest people go and kind of go and network, go and meet these people. These are going to be the people that are going to be your future, bosses or research administrators or colleagues or whatever. A lot of times we talk about, I'm going into my tirades, I probably sound like your parents, but we go on a lot of neat trips to, California and San Diego, and I'm going to Hawaii, going to all these neat places, but I'm not going to be working with people in Hawaii anytime soon. I'm going to be working with these folks right here. You live around here, you're going to be dealing with these, maybe not Ohio State, but there was a reason that guy was here. Maybe he did his PhD down here or knew someone who knew someone down here or whatever. These are going to be the folks that you're going to be working with. So I really strongly encourage you when, we love going out of town, and you guys went to Atlanta or something like that one time, and Georgia and all this, Atlanta and Georgia, the same thing. I took some students to Atlanta last year. Those are all good and well, but some of these local things that are low-hanging fruit, especially I didn't have to pay a dime for something like this, are great opportunities to go and meet and kind of be exposed. Most of this stuff is probably a little over our head, but you're going to notice some of the maps that we're looking at, talking about, and all that other good stuff here. And so, I want to kind of push those things. A couple of weeks ago, I talked about the position paper. Just start thinking about a position paper. Basically, what we're going to start doing today is inferential statistics, and I'll explain what those are, but no more means, medians. I assume everyone knows what they mean. And from looking at the exam, I think we've got a good grasp of those, of the means. I got a little concerned about Z-scores. I saw some really wacky Z-scores, like negative 82 or 54. These Z-scores should be between about -3 and +3. And so we've got this little formula right there. Make sure you know how to apply it. It's okay you get it wrong in the exam or whatever. Let's not get it wrong again here. And so during the exam, we had this up here. Make sure you know how to use it, know how to apply it. You can manipulate some of these things in Excel, especially since we provided the kind of spreadsheets and everything beforehand. So you can kind of go through and calculate and get used to it. I didn't really kind of switch the exam around too much, but for the most part, the exam looked pretty good. I finished grading a lot of it, but someone had a family emergency, so I'm not going to avail all the answers. I'm not going to avail the answers just yet until they take it. To keep everything on the same playing field. But we got the position paper rubric. I'll mention this real quick. This is for any graduate student or undergraduate student who wants to eventually take this class as a graduate class. So if you're signed up for the graduate version of the class, you can do it. Also, if late next year and you're like, hey, I think I want to go back to grad school, you don't have to retake this class if you took it as an undergrad. All you have to do is the position paper. And so people are taking this as an undergrad class and come back later. Basically, if you get an A or a B, you're just going to get the same grade you earned as the class, and then I'm going to average it in with what you get on the position paper. So I'll have all these things. So if you had an 88 and get 100 on the position paper, that B that you got with me as an undergrad will turn into an A. But most of the people are kind of signed up for the grad version of the class as well. So we got this position paper, and the whole goal of the position paper is basically you're going to prove or disprove something. And so a couple things that I have here. So things like cancer mortality rates are concentrated in certain regions of the state. And so this week we're going to talk about inferential statistics. Next week we're going to talk about t-tests, where I make these statements where I say, income in rural areas is higher than or lower than income in urban areas. That's a perfectly, can we prove or disprove that? Definitely. Now, what if it's the average is 40,000 versus 39,000? Is that a small difference? And based on sampling biases and all those other things, it's going to be difficult for us to make those statements. So we're going to talk about things like margins of error and all that other good stuff that we can authoritatively make those statements. And so you're going to write a 6 to 8 page paper that just goes through and you use the methods, you develop the data. We have a lot of GIS projects sitting here right now. We've got some crime stuff out there if anyone wants to utilize that. I'm really kind of, COVID rates change between urban and rural over the course of the pandemic. And so we're going to use some of these descriptive statistics here. You can see a couple examples of papers that I have right here that we're going to utilize the skills here. I've got paper. I forget exactly what these papers are for, but we've got the position paper, and this will be due on the 28th of November. And so it's just a quick little 4 to 6 page paper where you're going to prove or disprove some fact. It might be people who, you might use your paper that you did in 4010. People who live in, the recipients of what was it, food pantries, right?
So, there were two projects. Force-10, that was that field mapping?
Yeah.
So field mapping, I did, it was.
4010 was applied GIS. Yeah. I thought you did, we mapped the, no.
For I did a bunch of stuff.
Yeah.
Last semester.
The recipients, I'm thinking of maybe the field mapping one, with the recipients of,
I mapped grocery store prices around one of the block groups.
Okay.
Or census tracts.
Okay.
So I mapped grocery stores around the census tract where the food bank I work at has the most concentrated customers, but people who we serve the most. The census tract that the food bank is located in, and which also has the highest concentration of people who we serve, what the grocery store landscape was around that census tract, and there was only one grocery store within a Euclidean mile of the border of that census tract, and it had significantly marked up prices.
That's something we can look at, probably expand it out just a little bit, meaning, let's look at the 3 or the 5 within your recipients versus your non-recipients. Because today we're going to start talking a little bit more about sample size, meaning, all right, we've got one store that has high prices. That's not going to tell as much of a story. It's not going to tell as much of a story about as, okay, let's look at the 10 block groups that have the most recipients versus 10 block groups in Durham County that have none of your recipients, and let's compare those distances or whatever, and we'll get into that a little bit next week. But making authoritative and concrete statements is what really the focus of inferential statistics, two-tailed t-test. This is what people want to say. You read in the news, these days, you read in the newspaper, and we see things like, kids with college degrees make higher income than graduates who don't have college degrees, and what do people always say? Well, I know someone who, ... You know what I mean? What's the difference? Is the difference $50,000 versus $49,000? That's not much of a difference. Or is it $55,000 versus $45,000? That's a big difference. And that's what we're going to start talking about today, so that we can authoritatively make those statements. And so we're going to throw in normal distribution and z-scores and all those other things, and how those can be represented graphically. And so we've got that position paper. A couple of people have approached me about topics. My main thing is just find an idea that we can prove or disprove using the things that we do in class. You could do some things with descriptive statistics where, hey, let's look at the 10 most densely populated block groups that have food desert recipients, and what's the average distance and travel time to the nearest convenience store. For this one, it's 8 minutes, 6 minutes, 5 minutes, 4 minutes, 3 minutes, 2 minutes, versus the 10 highest income block groups in Durham County, and see if there's a difference between those. you know, and then we'll be doing something called a two-tailed t-test that says, hey, the average of these block groups versus the average of these block groups is statistically different or the same or whatever. So, you know, those are some things that we can kind of start to look at. Some things we can look at. So today we're going to talk about analyzing point patterns. And then today we're going to actually look at a project that one of my former students did, who was out at NC State, who was at NC State, is working on it. He was looking at things related to deer vehicle collisions. And he just reached out to me, and he works as an estimator. I don't really know what an estimator does, but they use GIS and they make a lot of money. So, you know, he said, I make a lot of money because he did real estate mapping previously for a real estate firm that went and purchased properties. And so he would go and map, you know, the recently sold, on sale, whatever. And I think an estimator is someone who does the same type of thing, but uses GIS, Excel, statistics, all those other things to figure out where we're going to buy land, where we're going to not buy land, all those other kind of good things there. And during the break, I'll probably think, but he reached out to me this weekend. So I'd like to have him come and kind of talk to you all about some of the things that we're doing. So today we're going to talk about point pattern analysis. And the reason why we can't just run means, medians, mode, standard, you know, all these numbers against each other, because I've got a map here of large supermarkets here in southeastern North Carolina. You can see there's a couple of 100 of them sitting here. I can see, you know, Rhode Island, this is the Modified Retail Food Environment Index, which is basically the percentage of stores that are healthy food compared to unhealthy food. And then I can see percent of mail-in ballots. So you can see it's high over here, it's low over here. Mail-in ballots basically mean the people who literally mail in their ballots, and then I can turn these into cluster maps. This is what we're going to be doing in a couple weeks. We're going to make these nice, pretty cluster maps, because I look at something like this, and I can turn it into something that looks like this. Who wants to look at this? I do. Okay, this is a cluster. I talked a little bit before about what a cluster is. What is a cluster? It's high values. What's high mean? When I talk about high value, what's the definition of high? I'm getting really abstract today. High. What's high mean? High temperature. What's high what day has a high temperature? Give me an example of a high temperature. 95? Well, why is that so high? What makes it so high? It's above what? Low temperature is 30. What's somewhere in the middle? What's in the middle? What do we call that? The mean or the median or whatever, the middle or whatever. So those measures of central tendency. So they're going to be really high or really low according to those measures of central tendency. You all know how to calculate median and mode and mean and all that other good stuff? I hope so. That's the whole exam about. And so these hotspots are areas that are surrounded by. Now, what's the definition of surrounded by? And so there's a lot of kind of layers to peel back. We'll talk a little bit more about later. These are clustering of COVID-19 incident rates as of 10/31/2020. So around the time of the general election, because we run into some challenges when we start doing things like change detection analysis and density and all these other things, where that if I look at the density of grocery stores versus farmers markets, there's a lot more grocery stores. So the density of grocery stores is a lot more than that of farmers markets, right? Just by definition. Okay. We have something like RFEI, the Retail Food Environment Index. Whew. Okay. This gets really wacky really quickly, but rural areas have many zero values because food sources are sparse in these regions. That's what you all said, the definition of rural. Not a lot of stuff out there. Low population density. Why would we put supermarkets out there if there are no people? But we run into some challenges when we do this. The Modified Retail Food Environment Index, once again, the average distance to the nearest food source, where most of the time we measure Euclidean distance, which is straight line and easy to commute, but They're also in absolute terms. So if I say it's from 10 minutes from my house to the nearest supermarket, is that a lot or a little? Little? Depends. What about right here? If I said from the NCCU campus to the nearest supermarket's 10 minutes away, what would you all say? Do you think Duke, kids over at Duke or, Chapel Hill, do you think they have to drive 10 minutes to the nearest supermarket? Mm-mm. You say it's really far away. Kids who live on campus and don't have access to transportation, they're gonna have a problem getting healthy and fresh food, unless they go over to the cafeteria. And then things like COVID-19 rates grouped at the zip code. So the appearance of higher and lower based on how the map creator dictates the classes on the map. And so who created these classes right here that go from 13 all the way up to 32? Who made this map that made these classes this way? Who made this map? I did. Yeah, me. I made it. So I could have changed this so there weren't that many high values or weren't that many low values. I could change these classes and colors and all these other things so it didn't do this, or that when we start to look at inferential statistics, these patterns are going to be, these are the patterns, no ifs, ands, or buts. And so when we analyze spatial patterns, these are all pretty much going to be quantitative in nature. And so when we do hotspot analysis, we're going to look at high values surrounded by other high values. And so in a couple of weeks, we're going to talk about mapping clusters, and we're going to look at things called LISAs, local calculations, local indicators of spatial autocorrelation. We're going to talk about this big fancy word called spatial autocorrelation. Has anyone heard that term before? We will soon, because all it means is that high values are near other high values, low values are near other low values. The stuff around here the stuff closer to here is going to contribute more than the stuff further away. Just like I said before, when we go network, I go to Hawaii to go to that conference, I'm probably never going to deal with anyone there again. I go to a little conference down the road in Chapel Hill, I'm going to see these people time and time again. And it's what we call distance decay. Has anyone heard that term before, distance decay? Okay. The things that are closer to you are going to impact you more. Okay. The crime rates around here are going to be pretty much all about the same. And as you get further and further away, they'll be impacted by some external or confounding factors. And so today, we're going to talk about some global calculations, meaning they describe an entire data set. Okay, we've said that before. What's an example of a describe an entire data set metric? Mean, median. What's an example of a local metric? Z-score. Every county has its own individual Z-score that you can go through and calculate based on the value at that county, the average, the arithmetic mean, and this little thing down here, that little theta thing, which is the standard deviation. You can calculate the standard deviation in the mean? You bet. You don't have to calculate it. I'll do it for you. And so we can use spatial statistics to determine feature distribution. And typically we look at clustered features versus dispersed features versus somewhere in the middle is what we call random features. Because I used this big fancy word before called spatial autocorrelation, which is just the manifestation of Kobler's first law of geography, which says that everything is related to everything else, but near things are more related than distant things. And so when we look up the temperature, I live up in Summerfield, a little north of Greensboro. I don't know the exact temperature where I live, but if I know the temperature 10 miles away, that's probably going to be a good indicator as opposed to the temperature 50 miles away. Right? And that's what we call spatial interpolation, spatial extrapolation. So we can use similarity, the degree to which characteristics of one location are similar or dissimilar to those nearby. So income, crime rates, race, ethnicity, everything that you can kind of think of, especially that can be normalized, the stuff around here is going to be related to this stuff down the street, and it's going to kind of change as you get further and further away. We can use correlation. Correlation is a variable within itself throughout space. Did you all do something did you all kind of map death rates versus median age? Did you make a little correlation? And basically you said, as the median age of a county increases, the death rate increases. Does that make sense? No, why? Because older people. Now, we don't, when we do our position paper, we don't want to do that no dust stuff, right? We don't want to say, hey, I bet you cancer death rates are going to be higher in older counties. Because what do you think I'm going to say? Sure, that makes sense. Yeah, sure. That makes sense. So does anyone remember what we did in order to kind of get rid of the effects of age and look at cancer rates? Normalize, and especially we did something called normalized by age. We did something called age adjusting or age grading so that the average age of each county was the same. Okay, and that gets a little ugly a little quickly. And so, like I said before, I've got temperature stations over here. I want to know what the temperature is here. The impact of these stations, in addition to other factors, is going to be a lot more than it is further away. So everything is related to everything else, but near things are more distant or more related than other things. And so we have things like positive spatial autocorrelation. What's that basically mean? High values near other high values, low values near other low values. And basically, we're going to have things called Moran's eye. We're going to have local Moran's eye. We're going to have things called hot spots and cold spots, which basically just take off from this concept where that we can kind of graph these things right here. Now, who wants to look at graphs? What do I want to look at? I want to look at nice little maps. Then we have things like negative spatial autocorrelation, which says I got a checkerboard pattern because that's the worst thing in my world. Okay, I look at AIDS mortality, cancer death rates, birth defects, ADHD. I see the highs near the highs and the low near the low. I don't like looking at stuff like this. I don't like looking at checkerboards where sometimes I got high near high, but medium near high, low near high, or whatever, because there's a distinct pattern when it comes to clustered, meaning they're all together. There's also a distinct pattern with dispersed. You know, imagine throwing 50 points up onto a map or up on here. You're going to have some highs near highs, lows near low. You're going to have points next to each other. What are the chances you're going to have points evenly distributed or evenly spaced apart? Really, really small. But that's going to be totally different than clustered. And so we're going to kind of look at this continuum, which are slightly different. Because what we talk about today is called inferential statistics. Basically, we're using statistics to do what? Test a hypothesis. What's an example of a hypothesis? You hear about this in the scientific method in 9th grade science class. What is it? What do you need? You need data and you prove, disprove. Give me an example of a hypothesis. We see these all the time. What's an example of hypothesis? Something you see on the, it doesn't even have to be GIS.
Fish can't swim up dams.
Fish can't swim up dams. We hear about this with school. What do we say? Schools in this county have higher achievement rates than schools in this county. Really easy. We hear about this all the time, or within certain parts of county. Northern and Southern Wake County have much higher school achievement rates than the actual city of Raleigh. Can we prove or disprove that? You bet. We got the data. And then what we're going to talk about here are the tests so that we can look at this. So we're going to use kind of assumptions that data come from a random sample or randomized experiment. As with these, statistics have clearly relative large number of cases. And like I said before, I can say, hey, the average height of the NCCU student is taller than the average height of the North Carolina AET student. Do that, right? That's a hypothesis. Can you prove or disprove that? Let's go start measuring people and get an adequate sample size and see if that's true or not true and reason why or whatever. But those are all examples of a hypothesis that we can prove or disprove. Now, it comes from a random sample. If I made that assumption, I went and picked out the basketball team to use as my sample. Is that really a random sample? No. What's the word random mean? We hear this term all the time. Random. Is there really any such thing as random, to be honest with you? Lacking a pattern. That's probably the best thing. Lacking a pattern. A lot of times when you take, I'm working with Durham County right now on a project where they need to go and fill out some little code. They take a little code and they're doing water quality or something like that. Water quality survey where they got to use a little code, and it takes them to this survey that they fill out how they feel about water quality education. That's really not random. Why? Why isn't that even a random survey? In order for you to take the stinking survey, what do you need to be able to do? Know how to use a little QR code thing, right? So how many people is that going to get rid of? A lot. My grandmother, everyone else who doesn't know how to use it. Or people with the flip phones or whatever. And so when you start to create data, and I think I'm speaking a little bit to Benjamin here because, we're thinking about, all right, I want to go collect, I want to have everything consistent. I want to go to all these different stores right here and collect staple prices or whatever. And so, I want to make sure that the playing field is equal for all of these. And these days we've got things like Survey 123. You've done Survey 123 before. We've done things like Survey 123, where we can go collect pictures and drop downs and everything else using literally turn this thing into a survey tool. What are all the things that you are going to want to collect so that we maintain consistency? I know Alondra collected a survey of all of the fast food restaurants around her high school, right? Around her high school a couple years ago. And, we went and mapped those. So we can collect quantitative as well as qualitative information, the pictures and all that other good stuff. Okay. And then we have confidence intervals because we see things like presidential elections. They want this person 47% plus or minus 3%. Why? Because we're not going to go and measure the height of every single NCCU student. We're not going to measure the height of every single North Carolina A&T student. So we take these samples and hope they're good enough, even though we see things like the 2016 election where we thought one person was going to win, and that confidence interval, they kind of overlap with themselves. Now, there's no correct method for inference from data collected from a bias of unknown size. And so when we do our water sampling testing, it's already biased because it's already limited to the people who, one, want to take the survey, and then two, who know how to actually use a little code, and then three, who bother to actually go through and collect the survey. So there's a lot of layers. There's a lot of layers that go through on this. And so the mean is strongly influenced by a few extreme observations. We know that already. Outliers can have a large impact on confidence intervals. So we can look at things like this. Now, we've seen this before. Okay, we've got this nice little normal distribution here. And when we work with normalized data, this is typically what we look at, whether it's football wins or median household income or crime rates. It looks something like this when it's normalized. Now, for the exam, some people were kind of talking about the idea of normalization. And I asked about rates we're using per capita versus per 10,000 or 100,000. Now, those are two slightly different questions. So make sure you don't conflate these. But we talked about the idea of z-score. Can we calculate z-score? Of course we can. Z-score equals the value minus the number divided by the standard deviation. And so when we look at really, really high z-scores, which are really far away from the mean, this is where we start to get significant, meaning I've got a distribution of distance to the nearest supermarket for low income versus distance to the supermarket of high income. And we have two different sets of distribution. If these sets of distribution are far enough away from each other, they're not going to overlap with each other. We can say, hey, there's no overlap. This mean and this mean are two totally different things, and we can say they're statistically different. If they're right next to each other, they're going to kind of overlap. And we have a lot of these tools that say that. So we could say with 99% significance, with 95% significance, with 90% significance, with 80% significance. Then most of the time when we do research, we like things at 90% significance or better, where I get plus or minus 1.65, 1.65 standard deviations away from the mean. So we're looking at things that are over here, things that are over here. Essentially that this distribution surface of your incomes for one set of data is far enough away that these things don't line up. But we'll talk about that a little bit more next week, because we like to look at things like this, because our ArcGIS Pro software gives us nice, pretty distribution curves that look like this, confidence intervals and p-values and all this other good stuff. And we're not going to get into the math. We're going to just figure out how do we interpret these things here. And so I can look at this, and like I said before, typically with our normal distribution, we can look at the percentage of stuff, percentage of phenomena that lie within 1, 2, and 3 standard deviations. And so when I see, it gets a little unsettling when I see the exam and people are putting like 42 for a standard deviation. Where's 42? 42 is way over here. We're looking at like -3 and +3 based on these. And we're going to have some real, we're not going to have too many of those extreme cases. Because what we're going to do is we see a bunch of points up on a map. That's what we're going to look at today and then build from there. Now, how do we know they are distributed? How do we know if they're random, dispersed, or clustered? You're just going to look at them and figure them out? Okay, we got a couple of different methods. We have something called quadrant analysis, which I really like doing because it kind of brings in our GIS skills. I have a little button here called nearest neighbor. And then there's something I don't really like doing too much. It's called pay function. I'll mention it here. It's got different advantages, disadvantages. We'll talk about these here, because what we're going to do is we're going to look at a set of points and we're going to see if they're, well, how clustered are they? How dispersed are they? How whatever are they with statistical significance? So we can say, hey, statistically, this is dispersed versus random versus whatever. And so we have something called quadrant analysis. I got formulas right here. Okay. Now, quadrant is basically a square. It's just a little square on top of things. Now, why would I want to superimpose squares on top of stuff? Like I want to count, and we're putting together some things. Dr. McGinn and I are teaching a crime analysis class next semester. And instead of using block groups and tracks and zip codes, they start to use squares and actually hexagons. Why do we use squares and hexagons instead of actual block groups? What's the advantage of these? I'll just talk about square for now. Hexagon better approximates a surface area, better than a square. But why do I use squares? The same size. And so if I know that this square has 23 crimes and that square has 28 crimes and that square has 30 crimes, I know the square with the most number of crimes has most number of crimes. I don't have to normalize by area. Now I can deal with stuff with population and all that other stuff later, but they're all the same size. And it also looks like a nice raster map as well. And so I can superimpose these squares on it. Now, how big are the actual squares? Okay, and I can use this little formula right here. And we're going to go back and revisit this, but this is the length of each square is the square root of 2 times the area divided by n. Just another formula. We know what 2 is. Area is just the area in miles or square miles. N is the number of features. And then we just take the square root of that. And we're going to talk about the reason for that in a little bit. And then I've got this nasty formula here, which is going to basically, I'll show you what it's going to do here, but it's going to approximate a nice little normal distribution curve using this other number here. Do we care about what any of this stuff means? No, because guess what we're going to do? We're just going to bring it into Excel. And this is going to be what we call a Poisson distribution. Because when we do quadrant analysis, we want to look at if it's a random pattern or if it's a clustered pattern. So I look at something like this. I can see a lot of this stuff here is kind of up in the northwest portion of this, while this is more evenly distributed. I've got a 1, a 3, a 1, a 2, a 1, a 2, no zeros here. Well, I've got a 4, a 3, a 3, a 2, a 1, and a bunch of zeros here. And so this is what quadrant analysis does. I go and superimpose a bunch of squares on these things, and then I can start to count the number of squares that have 1, the number of squares that have 2, the number of squares that have 3, and look how it would be according to a random distribution of me just throwing the same number of points up there and seeing how it falls. Okay? And so another, to me, inferential statistics is how do things compare to random? Okay, how do things compare to random? How does a phenomena compare to random? If I had income pattern up on a map, or if I had AIDS mortality or suicide rates, how does that map compare to what a random map would look like? Can I make a random map of AIDS mortality? Of course I can. I can just create some random numbers, pop it up there, and see how different they are using a little bit of change detection analysis. So I can do the same exact thing here. Now, this might be deer vehicle sighting. They might be crimes. They might be any sort of point pattern phenomena. Next week and the week after, we're going to talk a little bit more about the clustering when we group things by polygons with COVID rates. But we're starting kind of small right here. And so now with quadrant analysis, and I gave you that formula before because, well, quadrant size is going to be important. Okay? If quadrant size is really, really big, that means I don't have that many features here to actually have spatial integrity, spatial relationships. You know, if you have a map with just like 2 counties on it and it only shows 2 values, is it really a map? No, not a map. You know, it's not a map because what a map do? It shows spatial differentiation. You know, I have a really small quadrant size. I have a whole bunch of zero bugs. And so this is kind of like the Goldilocks phenomena where that I want to make a quadrant size that I've got some zeros, I've got some 5s, I've got some 2s, I've got, whatever, that distributes a normal distribution based on the number of points and the number of quadrants. And there's another little formula that we throw in right there that we kind of talk about. And so this is too small. We have a lot of quadrants with 0 points. This is too big. It doesn't have a lot of quadrants. And then this one's kind of just right. Because the big problem we have when we map crime of Durham, we have 30,000 points. What does it look like? What does 30,000 points really look like on a map? It's not real. It's just a big blob of stuff. So, we can group those by zip code or group those by block groups with population or whatever. But to me, this is another way that we can kind of go and address this. And to be honest with you, things like deer vehicle collisions or volcanoes or tornadoes or more physical phenomena are probably going to be a little more suited for quadrant analysis because they're not going to be constrained or counted by block group boundaries. We don't care about how many tornadoes per 1,000 people exist. We care about things like tornadoes per square mile. So if we create quadrants, we don't really have to worry about the per square mile because that kind of gets addressed by creating equally sized squares. Another word for equally sized squares is called a lattice. Lattice. Has anyone heard that term before, lattice? Oh, you just heard it. Okay. And so I can start to kind of run these formulas right here where I can create the quadrant size in feet, the number of quadrants, the number of points per quadrant, the average number of sightings per cell, so that we can start to figure out what are the chances that we're going to have 5 in this, or 4 in this, or 3 in this, or 0 in this. And so we can compare it to a normal distribution curve. Now, I really like doing this because this thing is called the Poisson distribution. It's a frequency of counts compared to the frequency of a random distribution of points. Okay, see if differences exist. So basically, I can look at a kind of normal distribution right here, the average number of sightings per quadrant, and basically see how they compare. Now, this is an example of one here where I look at farmers markets within southeastern North Carolina. So these are farmers markets. And you can see that I kind of group those by quadrants. So I create my quadrants. Is there a way that I can count the number of farmers markets represented by these green dots by each of these polygons? Can you do that? How are you going to do it, Alondra? Select by location one by one, or we can run a spatial join. Yeah, we do spatial joins all the time, right? We started week number 1 doing spatial joins. So I can just run a spatial join, count how many each one appears, and then we can just run a summarize that says, for the zeros, I've got 23 zeros, I've got 17 ones, 18 twos, and basically all I'm going to do is create a nice little curve that says, this is what I've got, this is what it's supposed to look like. These things look really kind of the same, right? They look kind of the same. So we could say that farmers markets exhibit a Poisson distribution. Now, why do we care? Why do we really care about that? You know, I care because I want to see how the farmers markets look compared to the grocery stores and the convenience stores and everything, because this is going to have more access to more people. Meaning, I got some things that are close together, I got some things that are far apart, but when I look at a random distribution, that's the whole definition of random. Things are close, things are far apart. It would be kind of strange if they were all like equally far apart from each other, which doesn't happen in nature or reality. Now here's one for convenience stores. I do the same thing. Why are these quadrants smaller for convenience stores? Their neighborhood, and also, what was that equation? The square root of 2 times a divided by n. Now, if the area is the same and the n, what does n stand for? Let me use this word. I throw around this word n, but what does it stand for? That's all right. That's all right. It's my job to tell you. So n stands for sample size. Okay, it's the sample size. So there's a lot more convenience stores than farmers markets. Okay, so there might only be 30 or 40 farmers markets here. There's probably a couple hundred convenience stores right here. So if my denominator is higher, what's that make the number? Lower, right? We're doing some math here. Makes it a little bit lower. And so now what we do with this Poisson distribution is we look at this and we compare it. In theory, this is what the Poisson distribution looks like. This is what it really is. So what it looks like in green versus what it really is, we can see there's 2 different things here. Okay? And basically for the exercise that we're going to do today, I'm going to have you do a quadrant analysis at the end here. I post a really nice tutorial on that, because if we don't get to it today, because I want to focus on average nearest neighbor, because that's something that's pretty easy to do. I've had some students do some really neat work with this. I've had two projects in particular with A&N, which I think is really good. Okay. So the other thing we've got here is nearest neighbor index. This is really easy to measure. What do you think nearest neighbor index measures? How far you are to the nearest neighbor. So nearest neighbor index is used to identify groups that are spatially closer than what could be expected. Expected is just another word for what? Random. And so imagine I throw a whole bunch of points up here versus what I have here. So this is what I mean by inferential statistics, meaning what do I expect? How is this set of points going to compare to random? Okay, so I throw random points up here. Some will be far apart, some will be, well, they'll probably be scattered throughout the entire thing here. Now some caveats here. Each point is a distribution, the shortest distance to the next closest point. The minimum distances for all points are just added together, and the sum is divided by the total number of cases. What's that? Didn't we talk about this before? Add up all the numbers, divide by the total number. All we're doing is just figuring out how far each point is to the nearest neighbor, adding them all up and dividing by the total number of points. So average nearest neighbor analysis is usually sometimes called ANN. The average nearest neighbor. And then we create a random distance. And so we have a calculation out there that all we're going to do is just compare this set of points to a random set of points and see how far they are from each other. You know, are they really close? Is the average distance 4,000 meters versus 4,050 meters? It's probably not enough of a difference. And so we'll look at what this does here. And so you can see, okay, the distance from this point to this point, distance from this point. Now this is just Euclidean distance, right? Euclidean just means straight line. Do we know how to calculate Euclidean distance in a plane? Everyone should be nodding their head yes. How do we calculate that? Let me pick on someone here. Okay, let's see. Tamar, how do we calculate Euclidean distance? I don't know if they can see me. Uh-oh. Maybe Tamar's not there. Kaya, how do we calculate Euclidean distance? Do you remember? This is why I don't like virtual stuff. But. All right. Remember the square root of delta x squared plus delta y squared, x1 minus x2 squared plus y1 minus y2 squared. And just take the square root of that. Okay. So this is from geometry class. It's kind of like the Pythagorean theorem, x squared plus y squared, the square root of x squared plus y squared. Yeah. That's the same thing where basically with the Pythagorean theorem, you got your 0, 0, 0, 0 is your one of your points right there. And so it's just kind of a representation of that in a flat plane. And once we start doing this 3D stuff, it gets really, really ugly. So all we do is just go and average this up. And so when we run this nearest neighbor index, is that the nearest neighbor index is the proportion of the actual distribution of points compared to a random distribution of points. That's all it is. It's just a ratio. And so if the result is around 1, that means they're randomly distributed. If they're less than 1, we've got clustering, meaning that these points are closer than what we would expect them to be. Then obviously, if the nearest neighbor index is greater than 1, we have a uniform pattern. And so this continuum, we're not really going from kind of clustered to unclustered. We go from dispersed to random to clustered. And that's going to be one pervasive theme that we're going to see in inferential statistics that we're not really used to in like math class. We go from high to low. In statistics, we don't go from high to low. We go from like cold spots to no relation to each other to hot spots. And cold spots and hot spots, they're not any better or any worse than each other. They're just one's low values surrounded by low values in relation to the mean with the descriptive statistics that we had already talked about. And so when we look at this continuum, we're going from dispersed to random to clustered. And that's important. All right, who wants to see some formulas? No one else does either. Okay, but you can see the square root of n over a, and basically I like showing these things here just so you get an idea of the observed versus the expected. Observed versus the expected. This is some sort of average right there. And so all we do is just average things up. And then we have all these nasty numbers here. But to me, what I care about is the result. So when I look at the nearest neighbor index for something like convenience stores, this is convenience stores, nearest neighbor index, I'm going to run the tool and it says the z-score is negative 24.1677. What would happen if someone told you the z-score was negative 24.167? Is that close to the mean or far from the mean? A lot of varies, we'll just say. Very, very far from the mean. And so it says here that there is less than 1% likelihood that this clustered pattern could be a result of random chance. And so I bet you we're looking at something that's very, 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 lots of varies clustered. Okay, and it's basically telling you there's really no chance that this set of points that we're looking at for convenience stores is clustered. It is clustered. It's not random. Now here's another one here that we see. Okay, and so that z-score can get converted to a p-value. See that p-value up there? That is the chances that it's random. 0.0000000. There's a lot of zeros there. And most of the time, when we talk about these p-values, you can't really say anything is truly zero, but there are so many zeros here, there's probably a 1 here somewhere, but it doesn't want to talk about that. For another set of points here, the observed is 4,600 meters, the expected is 4,000, the ratio is basically 4,022 divided by 4,642, which is 1.15. I'm sorry, 4,642 divided by 4022, which is 1.15. It converts to a z-score of 1.67 and a p-value of 0.1. Meaning they're different. They're not different enough for me to say that these are clustered. Remember what I said. What's a good p-value? 0.1, 0.09, 0.08. And so the big thing I care about, because I don't want to look at this stuff here. What I care about and what I want you all to care about is what's the p-value rate? I don't even care about the z-score right here. I don't even care about these numbers right here. Okay, these things might be deer vehicle sightings. They might be mitochondria sitting inside a cell or something, something like that at a totally different scale. But they're all spatial in nature at the end of the day. Okay. What I care about is this p-value. Look at this p-value and make sure you're able to interpret it. Okay, and now when I look at it here, given the z-score of this, the pattern does not appear to be significantly different than random. Almost significantly different than random, but not quite. Okay, so for this particular pattern here. I'll talk about one other thing here, and then we'll take a quick break, and then we'll start kind of talking about the homework a little bit, because what we're going to look at is just a bunch of points. And the thing about these points is it's really difficult for our eyes to make sense of these. And that's why we kind of take advantage of these computers that allow us to do these large-scale calculations all in one. I'll mention this because this is one of the tools sitting there. I'm not a big fan of Ripley's K because it creates basically increasing buffers, but it looks at the increasing distances at specified intervals indicate what the distance of concentration of features is at the largest. All right, so basically spatial point pattern process based on the location of the event. So essentially what we're doing as we go further and further out, we are getting bigger and bigger using edge corrections and all this other stuff. So we can look at, hey, at this particular buffer, we have more clustering than at this particular buffer right here. Like I said before, I'm not a big fan of k-means clustering, but we can explain what it is. But you can see here, there's a lot of clustering here. As we get further out, we have a lot less clustering. But we're going to take a break, and what we're going to work on is exercise number 5. I'm going to leave last part quadrant analysis for you, but we're going to really focus on the nearest neighbor right here, and being able to extract the information. We're going to kind of revisit a little bit of our spatial join stuff, because for the swine lagoons, I saw a couple of problems with the swine lagoons where we were doing spatial joins and new column calculations. And like for Forsyth County, remember Forsyth County had nothing in it, and then it magically had a density with it. Like if it has no swine lagoons, what's the density automatically going to be? zero. But saw that, so I see some kind of disconnects between the columns or using the wrong columns, and really making sure you're able to internalize and generate those tables. Remember those tables that we kind of popped out there that I gave you ready to go? Make sure you're able to generate these. And I'm not sure everyone took full advantage of those. That's fine. If not, no big deal, because it's okay to get it wrong once. I don't care if you get it wrong once. What's the big problem? Get it wrong twice, more than once. And that time I don't matter. Doesn't matter. And so we'll kind of focus on that. Also, with the exams, while I'm thinking about, I'll scale up the exams. And so if you see anything sitting there now, it's going to be scaled up, just because we did have someone get 100. Did you get to see your score? Copy off of him next. But but the one problem with the exam was, you get one thing wrong, like for a set of questions, guess what? You're probably getting that whole set wrong. So a lot of times these things are going to cascade, meaning you get a whole section, all right, you just got 20 points off. And so I like to give a little bit of leeway with those as well. But I wouldn't be too concerned about those, because those will be scaled up. But I'd be concerned enough to hook up with me, hook up with Samuel, who is going to be one of our TAs in our free time, to make sure we address those, because I'm going to be talking about means and medians and assume z-scores. I just started throwing z-scores around here. You better know what a z-score is. Okay, so let's take 10 minutes. We'll come back at about 6:22, 6:23, and we'll start talking about that exercise. So if you haven't already, get that exercise up and ready to go, and we'll start talking about that. Oh, we got about 6 minutes here. Where am I? There's me. Hi. I got about 2, 3 minutes here. We gotta hook up about that project sometime. When are you on campus?
Night classes,
Okay,
I can be on campus,
let's make something next week. I'm gonna be off campus Friday, so. Or just WebEx, like, hey, we're gonna create this, I'll send you a link so I can start paying you a stipend and create we'll sit down, create a schema for a survey that I can kind of look at and we can map and all that other good stuff,
yeah,
so.
for sure.
I've dealt with a couple of folks who kind of, I don't want to babysit, so I think you'll be fine with, just going collecting the data and then figure out what we can do with mapping it and all that other good stuff, so.
Yeah, I can be here early on Wednesdays.
Okay, yeah, I'm here I'm here at 8 or whatever, but I'm here that early.
Early for me, so early for what would be like 1.
Oh, okay, that's fine. I just dropped me a reminder just so I can clear out my calendar.
I'll send you.
And I'll start getting you paid and all that other good stuff too, so I wanna get that, and I got so much money that I don't even know what to do with it, I wanna start spending it, but I want stuff in return. I'm at the point where like, I'll keep my money. I'll keep it if stuff's not getting done but I know you've done this before, so you'll be fine, so. All right, cool. Let me start talking here. So what we're gonna do is open up exercise number 5 here. In the meantime here, it looks like this. So it's a bunch of counties. It's just a bunch of counties and a bunch of points. These are deer vehicle collisions that I got probably about 10 or 11 years ago from a student named Eric, who did his undergrad over at NC State. And so this is Eric these days. And he was one of my first master's students in about 2010. Would you say, wow? Yes, everyone liked him because he's a weightlifter and he had like one of the biggest arms I've ever seen. Like he's like big arms, and he always drank water and all this other stuff. Really, really good shape, nice kid too. But came to us from ecology, and my guess was he probably sat in class, took all these ecology classes, didn't really know what to do with it, and was like, I want to do something with real world data. So we got a list of all deer vehicle collisions. We geocoded it because you can get an idea as to what it looks like. And then now you can see kind of what he's got going on here. He's a senior estimator, GIS consultant. He did his master's here. I started here in 2011. You can see some of his projects that he did. He was doing sighting hiking trails, change detection of impervious surfaces. So you can get an idea as to some of the stuff that he was doing. And now he works as an estimator. If we look at all nine of his experiences, he got his start. He got to start with doing 40-10, 34-35, 20-20, where he is a teaching assistant, where like he went and helped teach our classes. He was really good in front of the classroom. I've got a student named Samuel, so I'm going to kind of connect some people with Samuel when I'm not available to kind of instruct, help students, sit down for an hour or two here, go through some exercises and all that other good stuff. And he did a really good job with that. But he got his job kind of doing a GIS technician for City of Raleigh, geometric correction, reverse geocode, water distribution networks, organizational skills, edit, evaluated, map versions, all that other good stuff here. And he got into like a GIS consultant analysis and started doing project estimation. And basically, I got an idea. I Googled it real quick, but a project estimator, senior estimator for utilities companies, are the people that go and basically figure out how much it's going to cost to do a construction project. And so, we use, especially these days, we use things like, drones or whatever to figure out how much volume of earth physically needs to be moved. Because these days, drones, in addition to taking nice, pretty pictures, if we fly circles around these things and take these pictures at different angles, we can do volumetric measurements. And so we've got tools here that you can log in using our GIS software. We've got all this fancy software that allow us to do this. And so you can see he's been doing these kind of been doing this estimation stuff for years. Because like I said before, previously he did real estate mapping at one point in time. Maybe this was part of the, like kind of the GIS. It was part of the government, government job. But home sites, yes, this is what he did too, and he did work for HDI home sites. So he's doing like home site mapping. What is sold? What is the price of things gone up? But this is kind of the work here is kind of his baby here. So he's, doing real good. He's probably, early 30s or something like that, and probably makes more money than me, And you can see he uses ArcGIS, HAZUS. That's a Hazard US, which is if you take, there's a GIS class that Dr. V offers called, what's it called? Hazard Analysis with GIS. I think it's an undergrad class, but she teaches that using HAZUS, GRASS, which is open source, ENVI, which is a remote sensing software. So all these softwares that kind of go off with each other. I don't know the Ag Tech, Carlson Takeoff, or any of these other things. And so I don't want to kind of, I don't want to get too much into this, but this was his kind of baby right here. So these are deer vehicle collisions throughout, I don't know, a 15 county region right here. And so what do these look like to you? Bunch of points, right? And so we want to see if there's any spatial relationship with these. Are these evenly distributed? Obviously, you can see these linear features. They're going to be located along roads because in order for there to be a deer vehicle collision, there probably needs to be a road, attached to it. But, without any further ado here, it looks like a bunch of points that you or I can't really process. So we're going to start looking at the exercise right here. And when we look at this exercise number 5, we're going to look at the distribution of deer vehicle collisions in Caswell County versus Rockingham County. Okay, just the number of deer vehicle collisions in each of these counties. We could do some spatial joins to calculate these, but first of all, we're going to have to export these as independent feature classes. And this is kind of where I get a little, we're going to have to revisit some of our skills from 4010, or those of us taking this class for the first time, we're going to be learning these skills for the first time, Meaning, when we open up this map right here, who went and gave you all these feature classes sitting over here on the left? I did. I went and did this. And if we go to view, catalog pane, and I click on databases, and we open up exercise 5, you can see all the feature classes sitting over here. And so I have things like bad fishnet, because we have some things called bad fishnet, Caswell deer vehicle collisions, also Rockingham deer vehicle collisions, but we're going to extract these out ourselves. I also, I went and created these here. I got good fishnet, I got bad fishnet, because we're going to talk about the idea of fishnet. Another word for lattice and grid and cell is fishnet. That's the GIS tool to create it. And so we're going to extract out Caswell County versus Rockingham County. Now, where's Caswell County? Where's Rockingham County? This is a geography class. Which one is which? How do I figure out which one is which? How do I count the number of features within each? How do I do this? What are we going to start doing here? And this is where, some of the things we really start to talk about, where there's not going to be just one button you click on to get the answer. You got to start clicking one button to the next, to the next, to the next, to the next. And you click enough buttons in the right direction, we'll get the right answer. And that's kind of really part of critical and holistic, problem solving. And so the first thing we want to do is, all right, how do we figure out which county is which? The top 2. Okay. So she said the top 2 because you're a geography expert, right? Or I can right mouse click and click on labels, right? I can right mouse click and click on label. I can right mouse click and click on labeling properties. Why isn't it labeling? What'd you do wrong? Whose fault is this? Okay. All right, I'll do what Alondra said, and here we are. I'll go to map, and this is Rockingham County right here. Is that right, Alondra? Yeah. So we got Rockingham County. What are the different ways that you can select it? Well, one here is I can just go down to here and find it in the attribute table, sort it, and find it as well. You know, I can go to Caswell County right here, because the very first thing we got to do is data preparation. When I went and created all these feature classes right here for this project, do you think they were all just sitting right here ready to be used? No, I had to go through and prep all these, extract these from a state, extract these from that kind of the state website, extract out this study area, make these things nice and blue, create some of these fishnets and all this other good stuff. And so when you start doing GIS work, for the most part, what you're going to be doing is data preparation so you can make the nice, pretty map. And so this data preparation is a large part of doing things. Now, the first thing we're going to do, since these are going to be we're going to be doing two independent sets or calculations or whatever, we're going to extract out one, then we're going to extract out the other. So these things, we're going to do one versus the other to figure out which one is more clustered versus least clustered or whatever. So the first thing I'm going to do is Rockingham County. So I'm going to pick Rockingham County right here. How do I find all of the points that occur within Rockingham County? Because the first thing we're doing here, real quick, is I want to find the number of deer vehicle collisions per 100 square miles. So we're not even like, does this ring a bell? This question ring a bell from anywhere? From what? Exam. Instead of deer vehicle collisions, what are we doing? Swine lagoons. It's the same exact thing. So I want to make sure we're able to kind of translate what we did last week with this. Now I could go and run a spatial join on all this, but since we're extracting out the data sets, now how do I pick just the points within that highlighted county? Select by location. So I got to select by location. All right, I want to find what? All the deer vehicle collisions. Exercise 5 collisions that intersect with what? Counties. And click apply. No. Yeah. Now, how many deer vehicle collisions do I have? 370. Just for the heck of it, how do I answer this first question here? What are the number of deer vehicle collisions per 100 square miles? How would I calculate this? How do you calculate this? What's the formula here? I'll kind of turn you all over here. How many deer vehicle collisions are in the county? 370. How many square miles are in that county? Can you tell me how many square miles are in that county? The attribute of the county's feature class. So now we're looking at two different feature classes right here. How many square miles are in that county? 572. And since I asked for 100, we're just going to multiply the whole thing by 100. So 370 times 100 divided by 572, which is what? 370 times 100 divided by 572, which is 64.68. Now, the other thing we needed to do is extract the points from the data set first, okay? Because we're going to run this whole nearest neighbor analysis on one set of data versus another set of data. We're going to see how clustered these blue points are versus the other county that Alondra pointed out for us. Okay? And this is another thing that we may or may not have done before, but now, under data, under the deer vehicle collisions, I can right mouse click. What do I have here? Attribute table, but I can go down to data and click export features. Okay. Now we need to pick the county. Now we can select. So what do I want to pick? I want to pick the collision. Let's finish that. Click. Oh, okay. So this is 371 because the county is selected. 300. Okay. Mario made a really good point in that over to the right here, there's 371 selected features. But now when I look at the attribute table under deer vehicle collisions, why did I only have 370, but it says 371 up there? Why? It says selected features 371, but why did I put 370? So why do I have 370 here, but it says 371 over here? Right here.
You selected the county.
Yeah, because the county's also selected. Okay, I'm just kind of pointing this to these folks here. You look at selected features right here. Those of you kind of joining us virtually, see to the right, selected features 371. But did it say number of deer vehicle collisions selected? No, it just said selected features. It could be counties, it could be crowns, it could be lots of other things that are highlighted in blue. Okay? And so now what I want to do is I want to go and extract out these features here. So I'm going to go export features. Now these days, this thing is nice and neat. So right mouse click, export features. My input features are my deer vehicle collisions. It says this input has a selection, records to be processed 370, right? We're going through the whole trouble of just exporting out these 370 because I don't want to run the nearest neighbor analysis on all, 1,200 or however many there are there. Okay, under output feature class, what database is it going to store it in? What's the name? This is getting real deep. What's the name of the database it's going to store it in? Yes. Okay. Now, when I go to the feature class, it says homework 5, that's the folder, but exercise 5.gdb. When you see something that says .gdb, that's what does GDB stand for? Okay, what do you think the G stands for? Exactly, geodatabase. And so we see that file geodatabase, and within the geodatabase, it's called exercise 5 export features. Do you want to call them exercise 5 export features? What is this thing really called? We're going to call it Rockingham, Rockingham DV collisions. So Rockingham DV collisions. Okay. And just for everyone's edification here, if we go to view and catalog pane over in the left here, you see these databases up here? this thing up there, say, you see the exercise 5.gdb? Okay, you see that little home base. What's that little home mean? Does anyone know? That's a little tricky. We haven't really talked about that. That's the default database. So when you export stuff like export features, it's going to automatically save it there unless you specify something else. Okay, that's where it's going to export it. So this is the database, but we can click on folders here, and then you can see my exercise 5 folder, which also has the database, but it's got some other kind of garbage and stuff here. That's part of this project here. So you can see all the feature classes that I have here. So you can also see like a Caswell fishnet that I actually already went through the trouble of creating back in the day. So hint, hint, when you got to do the quadrant analysis for, for Caswell County, it's kind of already sitting there. But, if you really wanted to, you can follow the tutorial and go through and kind of create your own fishnet. And fishnet is basically a lattice. Okay, next, what do we have here? Okay, so I've got my Rockingham DV collisions. We want to do the same thing for Caswell County. So I'm just going to go a little to the right. Now I'm being kind of smart about this stuff. You notice what I did here? I kept my select by location open already, right? So what I'm going to do here is watch. I'm going to go to my little map here. I'm going to go and select Caswell County. And now watch what's going to happen. I'm going to go exercise 5 collisions that intersect with counties. There we go. Look what I just did. You see what I just did? I ran the same thing again, but this computer, I just tricked the computer into picking, I went and picked Caswell County, went over and did it. Now we could run a spatial join for all these, but since we're extracting out those individual feature classes, I want to do this as well. Now, what is the year vehicle density for Caswell County? 115 times 100. How many square miles are in Caswell County? What's that? 428? 428. And so we'll go through and do this. You guys are 115 times 100 divided by 420. Why did I multiply through everything by 100? This is like 26.4. Why would I multiply through by 100? Is there any, does it matter if it's 0.26 versus 26.4? Does it matter at all? It's just readability. And especially when we do things like per capita, like 0.003 murders for, per person, instead of 3 murders for every 10,000 people. It's just readability. Nothing more, nothing less. You might have seen that question before too. Or might see it again. Okay, so once again, what we'll do here is we'll go to Deer Vehicle Collisions, right mouse click, Data, Export Features, and then we're going to just call these, I'm going to call these Caswell DV Collisions. And like any other good person, what I always do is when I don't need a data set anymore, I go and get rid of everything, change the colors so I differentiate between them, and kind of go from there. There we go. So this is what I've got here. Now, obviously, in this county, it's got a much lower density than this county. Did you even tell that between these two? I can't even tell that. Like the density of deer vehicle collisions in this county is about half that of deer vehicle collisions in this county. I couldn't even tell that just by looking at these. You know, because look what we did. We went through, that's what we actually calculated. If all the numbers that Alondra gave me were right, 428, right? So we've got these first two questions answered right here. Oh, that's something else. Okay, so what we're going to do, we're going to open up the tool to do nearest neighbor analysis. Okay, and we're going to use Euclidean distance. So all we're going to do is just compare one set to another. We're going to go over to analysis and click on tools. And I'm going to go to toolboxes and click on spatial statistics. And I've got a whole bunch of tools right here. I've got mapping clusters, modeling spatial relationships, co-location analysis. Okay, I got one up here called analyzing patterns. The very first one under analyzing patterns is called average nearest neighbor. What does it do? Calculates the nearest neighbor index based on the average distance from each feature to the nearest neighboring feature. So you can see some of these inferential statistics that we have here. This is the K function that I talk about next. You can run it, interpret it, look at these tools here. But I want to focus on this one here. So average nearest neighbor index. We're going to click on this tool here. And then all we're going to do is we're going to see which of the counties is more clustered than the other. So we're going to see if farmers markets are more clustered than supermarkets or more clustered than whatever. Because like I said before, I didn't even know, I honestly didn't even know that the set of points on the right had half the density of the set of points on the left. How am I going to know clustering? All right, so my input feature class for one is going to be Rockingham DV collisions. I always like to generate a report. Love generating reports. Why? Because I'll just cut and paste and screenshot it and use it for my teaching materials in the future. Okay. Let me finish this stuff. Okay. All right, we can click on the little button here that says, how do we measure it, all that other good stuff. How does it work? Use these formulas that we said before. All right, here we go. Ready? Down at the bottom, we'll click run. View details. What do we have here? The observed distance is 2088. Expected distance is 3276. The ratio, that z-score of -13, what does that mean?
It's clustered.
It's very, very, very clustered. Okay, very clustered.
This one was for the.
We did it for Rockingham. Yep. And it should say that in here as well. But now when I go, when I go to the folder here, there's a couple ways that I can go to it here. I can go to view, catalog view here. But now I can go to exercise 5, refresh it. And you can see homework 5, I should have something here that has an HTML page. And look what I got right here. So if I navigate to that, generate, that's what it generates for me. Do I really care?
You do that one.
Well, one more time where? When I basically in the output, it tells me where it stored the report. So if I click on generate report, I'll just navigate to where it generated the report. Yep. No, mine stored in the actual extracted folder. Yep.
And so it saves there, is that a PDF or?
HTML, like a web page. So you see it? Did you find it, Jayla? Or do you know where to find it? Where are you saving stuff here?
I just.
Did you do the generate report? Oh. Where'd you save it?
I have a question
Yep.
about the results here. So the Z-score,
Yeah.
what standard deviation is it using for the Z-score? For the whole data set?
Yes. So the average distance. So it has a whole bunch of distances. And so remember, the distance is a what? It's a no, the distance is going to be a number.
Yeah. Okay.
Just a number, 2.3 or 72,000, whatever it is.
Yeah.
So that's the standard deviation.
Just based off of the distances.
Yes. Based on the 370 distances that were calculated.
Got it. And
Yep.
then, so the mean
Is the average of those 370
average
distances. So the distance from each point to the nearest point. So I got point A. How far is point A to the nearest point? It's 2 miles, 3 miles, 2.1 miles.
Takes that average distance and then it takes the Z-score of the average distance.
Yes.
Okay.
Yes. And basically it's got a normal distribution curve and it just figures out what's the distance, average distance that it calculated versus a random distribution of points. Imagine we threw up a random distribution of points. How far is that distance away from, it runs a, doesn't do a Monte Carlo simulation. It does there's a formula in there that it can calculate with based on the number of points what a random distribution would look like.
So it compares it to like.
Yes.
Should be.
Yes.
What's the mean on that?
Yes. Puts the mean on that random and sees how far away those two means are from each other.
Okay.
Yes.
Makes more sense.
Whatever I just said to him, that's what it is. Everyone get that? That sounded smart. And we'll do the last one here. I've got to get out of here. I got a kid that's actually going to the hospital, so I get to. Yeah, it's going to be a fun night. So we'll do it again. This time we'll run it for Caswell, generate the report. I'll click on view details. I got a lower z-score here. Okay. What does the lower z-score mean? The other one was -13. This is -3.3. So which set is more clustered? Which set is more random? Rockingham's more clustered, yes. They're both very, very clustered, statistically clustered, but Rockingham is much more clustered based on what? The z-score. This one is actually kind of close to random, not that close based on the z-score. It's closer to -13, we'll just say. It's closer to -13. It's still clustered, but not as clustered as the other one. And so we've got that there. So what you'll be doing here is basically just interpreting the overall distance, z-score, p-value, which one's most clustered. And then we're going to run a couple of other tools here. The last one, I've got a really good tutorial on, for the last two, I've got a really good tutorial on quadrant analysis, because you're going to do a quadrant analysis curve specifically for Caswell County, where you're going to stick a fishnet on top of it and then count the number of times, count the number of points within each fishnet and the frequency. And then I've done that for a really good tutorial to kind of approximate what this kind of less random or more random is going to look like. Because in some cases, you want to run a Poisson distribution, it might say, hey, it's not clustered, but you run a nearest neighbor analysis, it's more clustered using nearest neighbor analysis. So you can kind of go through some different check boxes with some of these different metrics to see which one is which.
Strange. What's the projection of the fishnet? What projection does it use?
It'll use the one for the map, and you'll probably get to pick it as well.
Okay.
And so if I did my job right, if I right mouse click and go to map properties and coordinate system, this thing should already be in North Carolina state plan, which it looks like it is. Okay. And so I've got a good tutorial on there. Like I mentioned here, I've got a kid going over to Brenner's Hospital in Winston-Salem right now. So I am going to have a long night and I really need to go address that. But for exercise number 5, number 3, you're just going to be using the k-means function or Ripley's k function. And then 4 or 5, you're going to be using that extracted data for Caswell County, and then kind of go through my tutorial as to the process of doing a spatial join. You want to summarize. Has everyone run a spatial join before? You're in this class, you have. How about a summarize? You know what a summarize is. And so you're putting these techniques together so we can just create a nice Excel spreadsheet of curves and lines versus expected curves and lines using a Poisson distribution. So I wouldn't be too mad if you didn't submit this by next week, the Poisson distribution, but this is really powerful visuals to describe the spatial distribution of data as opposed to just some ratio and some z-score. And so I think it gives a little dimensionality to the results of those. So, okay. So that's it. I gotta hit the road here. So everyone else here, who joined us virtually. We'll see you all later, and that should be about it. So, see you all later.
Freddie Kitty's been.
I think so. Yeah, he's had